Okay, hello everyone. Sorry it's a little bit late. This might be a little bit longer, so just give you a heads up. I'm going to go over a lot of definitions, make sure you have a handle on it. So we kept going with our discussion of regression equations. And excuse me, what I'm going to do is just get started with the notes. I'll share screen. Okay, so here we go. Here is the definitions. So the regression equation, regression line. Basically, what we're looking at is we're looking at the line that minimizes the distance between the points in the line. So in other words, what I mean is, imagine we had a scatter plot and we have all the dots. What I said in class is there's no way that we're going to come up with one line that's going to capture all the dots. So basically what happens is we have a line that probably is going to look like that. And what it's going to do is it's going to minimize the distance of the residuals. And what a residual is, it's the distance between the line and the point. So from that line that we're going to use our projection, our prediction to that point, that area there is called a residual. So what ends up happening is we want to minimize this area of those, the square of those residuals, basically making squares. So all of these residuals are actually going to have a square. And the reason we square it is to make it a positive number. So what we're going to do is minimize that. Now, you will never have to do that. That's going to be something that will be done by the calculator or by a computer program. But I just need you to know that's what we're working with. So I'm going to quickly run through some of our definitions, and then I'll do an example that'll kind of highlight them. Okay, so first thing, when we write a regression equation, this is typically how we write it. And if you remember from your Algebra 1 days, we did y equals mx plus b. We don't do that anymore. We're going to do y hat equals a plus bx. The reason we put the hat on it is we're using it as a predictive model. So we put the hat on there to say it's like a prediction. If you don't put a hat on there, it's basically saying you're stating it with certainty. So like if you remember in Algebra 1, your line, all of those points were on the same line. We flip-flop our y-intercept. Our y-intercept was last in Algebra 1. It's first in stats. That's where we begin with. That's our y-intercept. Plus b is our slope. X is our explanatory variable. Now, what I said in class was, this is great, but what you really need to do is you need to define what y and x are. So what I'd recommend you do is this down here at the bottom. Predicted response variable in context equals y-intercept plus slope times explanatory variable in context, and actually put in those words. So like we did something in class where we talked about that, like sodium in calories. So predicted calories equals y-intercept plus slope times number of milligrams of sodium. That's what we did. Now, these are definitions. They're up on Schoology. The one thing I want to point out is when we look at something like this, anywhere where there's a bracket, you're going to replace something. You're going to replace words with numbers, or you're going to replace this thing with either the context from the problem or a number from the problem. So slopes definition, y-intercepts definition. What is the definition of linear? What is the definition of a positive association? What is the definition of a negative association? There are a lot of ways that you can do these three definitions. These ones, slope and y-intercept, those are pretty solid ones to use if you want to memorize those or kind of have those in your hip pocket. The next definition we're going to deal with is we're going to deal with a residual. We're going to talk about that on Friday, so don't sweat that if we're not going to go into that in any detail. We're going to talk about standard deviation of residual on Friday as well. Correlation coefficient we talked about last class. The interpretation is right there. It's basically the DOFC thing. This is really that DOFSC that we talked about. Coefficient of determination. I said this in class and I'll keep saying it over and over again. Please memorize this one above all others. We're going to talk about what it is in a moment, but I really need you to just have that memorized. There's just no other way to say it. So let's get to an example so we can kind of see this in practice. So this is typically how you're going to see it. So I just want you to be aware of how you're going to see it. This is what's called the data output table. We'll read the words up top, and what we find out is we're trying to predict calories based on sodium. So first thing I need you to understand is when you get one of these tables, the first thing, literally the first thing that I need you to do is I need you to just scribble this thing out. R squared adjusted, the ADJ one, to scribble it out. We are never, ever going to use that as an answer. So let's just get rid of that. Next thing, this table right up here, this part of the table, we're not going to worry about this until like March of 2022. So we're not going to worry about that right now. we're going to worry about these four numbers. So let me kind of walk through what the numbers are. Where it says constant, that number right there, that's my y-intercept. Or I have a number here, the 2457, that's my slope. Okay, so now what we're doing is we're able to kind of pull information from the table. This piece right here is always going to be your explanatory variable, your x value. So if I wanted to write this regression equation where we had that thing with the y hat, I remember on the notes it had y hat equals a plus bx. The way I'm going to write it is this: predicted calories equals y-intercept 147.1427 plus 0.2457 times milligrams of sodium. So that's how I'm going to write that. And that's what this is called, my LSRL equation. Okay. Next, interpreting the y-intercept. What does this number mean? And when I predict the y-intercept, I would say the predicted predicted value of calories is 147.1427 calories when sodium is 0 milligrams. So that's how I would interpret it. There's my context in my number. Basically, it's saying that if I had no sodium, I would anticipate or predict 147.1427 calories. Slope. The predicted value of calories increases. And the reason I'm going to say increases is because this is a positive slope. Increases 0.2457 when sodium increases by 1 unit, or in this case, 1 unit is 1 milligram of sodium. So I use increase when it's a positive. I use decrease increase when it's a negative. So there's my interpretation of slope. So we're going to talk about this on Friday. Next, that's this piece right here. That's the standard deviation residual. R squared. This is called my coefficient of determination. The way you want to think about it is it's roughly what % of the data is represented well by this equation. So it says a little bit more than half of the data is represented well by this equation. So a little bit more. Now, what I need you to understand is this is one of those definitions that you just got to regurgitate to me. When I ask you for the R squared, and again, this is the R squared, the coefficient of determination, I basically need you to say this. We're going to say 54.23% of the variation in my response variable calories can be explained by the LSRL of calories on sodium. It's a really awkward, clunky definition, I know, but this is one of those ones. There's only going to be there's 3 this year that I really want you to memorize. This is one I need you to memorize. The reason we do calories on sodium, it's your Y on your X, your slope. Calories is your response, your Y, sodium is your explanatory, your X. So your Y on X, that's why we have to say it this way. So again, what this is again saying is that this roughly says about how much of the data is well represented by the model, by this equation up here. So a little bit more than half. So this is actually an okay model. This is an okay model. Last piece we're going to talk about is the correlation coefficient, and it's R. And the way you get R from R squared is you literally take the square root of R squared, 0.5423, and it's going to be like 0.7 something. It's going to be 0.7 something. But if you remember your rules of square roots, there's a positive and there's a negative. The answer could be positive or negative. 0.7, I think it's 0.72. We look at the sign of the slope. The sign of the slope is positive. This becomes positive 0.72. So this tells me there's a relatively strong positive linear relationship between the number of sodium milligrams you consume and the number of calories you get. So there's a practice on the back that is up on the website that kind of, actually there's a practice on the website that actually goes through the little details where you can go through this. We'll talk about it again on Friday. So hopefully that helped. Have a nice